Okay, so the project one has been released, and I think that he arranged an online session for any questions you had regarding the project, but still, let me know if you have questions. Can you please raise your hand if you have any ambiguities related to the project? Everything is clear. You know what you need to do and what you need to submit. Okay. So if that is the case, then I'm not going to spend the time on explaining the project. So I'm skipping these slides. And if we have time, then I can come back to it. Okay, at that. Okay, so last time we were talking about inter-process communication, and we basically talked about the shared memory approach, shared memory mechanism. But we didn't have enough time to talk about the message passing mechanism and what are like pros and cons and how we can implement it. But before I start talking about message passing, any questions regarding the last week? No? Okay. So if you remember, we talked about the shared memory mechanism. And what we found is that if two processes want to communicate with each other, then they need to share the address space. Share the address space in the sense that the shared memory region is first need to be created by a process, and then the same shared memory region need to also be mapped into the address space of the other processes which are part of the communication. Okay, so but let's say we consider a case where the address space of the communicating processes is not administered by the same OS. So for example, let's say we have multiple processes communicating over a network. So in this case, there is not the same OS. The OS running on the client, it will be different from the OS running on the server. So if that is the situation, it will be difficult to achieve the communication between two processes using shared memory. So how can we then achieve the shared communication between the two processes? Second, the issue with this approach is that shared memory mechanism approach is that it places the burden on the application developer for implementing and manipulating the shared memory region. And by the way, when you will be working on your project, you will be like, you will have a more appreciation of this point because you will be responsible for implementing the shared memory region and handling it. So that burden is on the application developer. Also, since the address space is shared between the two processes, it is possible that, let's say, process A and process B are communicating through a shared memory region. And let's say that process B, it had some code vulnerability in its code. The person who was writing the code, it made some mistake. Like, for example, it didn't check the size of the buffer, and you are taking input from the user and you are not bounding the size of the buffer. So now a malicious person can exploit the buffer overflow vulnerability, and then it can, by using that, it can get the control of the process B. So now it can get the control of the process B, it can affect the execution of the process A in a malicious way. So actually, it means that it can be used, the shared memory region can be used as a security vulnerability in certain situations. So these are the issues we have with the shared memory region based approach for the communication between two processes. So on the other hand, why it is not appearing? Strange. Okay. Anyway, so the second approach which we can use is message passing, and the good thing about it is that it does not require the communicating processes to share the address space, and also the OS is responsible for implementing the mechanism. So there is less burden on the programmer or the developer to achieve the communication between two. Still, you need to make you need to write the program, but services are provided by the operating system, and you can use simply those services by making the system calls. Okay. But then there is a downside, since you are using the services of the operating system. So OS is involved, which means there is always a switch between you are always moving between the kernel mode and the user mode. because you are calling for the services of the operating system. So there is an OS intervention and there is more overhead as a result. Okay. Okay. So we are now going to look into details of how this message communication can be achieved. So with message passing system, these processes communicate with each other without having any shared variables, or in other words, any shared address space. Okay. So here is an example. So let's say that if two processes, P and Q, they want to communicate, they first need to establish a communication link, a logical communication link between them. And in this like set of slides, we are going to talk about only the logical aspect of the communication link. We are not going to talk about how it is physically implemented, because that is not the scope of this course. We are only going to talk about what are the logical approaches, and we will ask different questions. And then as a result of answering those questions, we will find that there are different approaches to establish the communication link between two processes. Okay. And once the communication link is established between two processes, then it can be used to exchange the messages between the two communicating processes. Definitely, even like, let's say even if the link is established between P and Q as shown in the figure, to initiate the message transfer, one of the process or the sender has to initiate it by taking some action. For example, by invoking the send system call, or by invoking the receive system call. Okay. Okay. So even like after the establishment of the link between the two processes, it doesn't mean that messages will transfer automatically, or they will be like they will be transferred all the time. So someone has to initiate the message transfer, and that for that the sender has to invoke a send API, a send system call, and the receiver has to invoke the receive system call. So with respect to the logical implementation of the link in a system, there are various questions which you can ask. For example, how sender specifies the receiving process and vice versa, which basically mean that how the receiver can specify the senders. So like, I mean, if I'm sending the message, am I sending the message to all the students in the class, or I'm sending to a particular person? Or similarly, if you are receiving the messages, from whom you are receiving the message. So how you can specify it, right? So one option is that we can specify the sender and the receiver explicitly. I don't know, I mean, it keeps breaking my flow of ideas. So anyway, so one option is that we can explicitly specify the name of the sender and the name of the receiver who are like going to be part of the communication. And which basically mean that we need to know the process ID of the sender and the receiver. I'm going to talk it anyway, it will keep coming. So otherwise it is wastage of time. So this is known as symmetric addressing. Symmetric addressing because the ID of the both the process, the sending process and the receiving process ID of the both processes need to be known. And in this way, a link is established exactly between two processes, which basically mean that a link cannot be shared among more than two processes. So if there is a link, then there will be two communicating processes, right? So here is like an example how you can, let's say you have a process Q, which is basically a sender. So you want to send a message to the process P. So you will invoke the send API, where you are specifying the ID of the process P and you are specifying the message which you want to send. And the message basically which you want to send, you will specify the pointer of that message. Similarly, if P is the receiver process, so it will invoke the receive API, but it also need to specify the sender, which is Q in this case, and the message, the pointer where the message will be stored. Okay. And here the P and Q, they are variables, but actually they are supposed to be the process IDs. Okay. So let's say now we consider a case that what if P, a process P, it want to receive messages also from other processes, not only from Q, but from other processes like R and S. So what does it mean? It means that since this approach allows only one link to be shared among two processes, so if P wants to receive messages from R and S, it's need to establish new separate links with R and S process. So it means that we need to establish more separate links, which basically means that more overhead and more potential underutilization. Why more potential underutilization? Can anyone tell me why I'm saying this, more potential underutilization? Because that's it. Yeah, go ahead.
If R needs to speak with E once, has to create a whole link.
Yeah. Yeah, that's correct. Let's say that P is communicating with all Q, R, and S, but it is receiving messages from all of them, Q, R, and S, but it cannot, let's say it doesn't have enough bandwidth to receive all of those messages quickly. So maybe it will be using only one link at a given time, and maybe the other once at a given time when one of those links is used, the other two links will be unused, right? So it will be basically underutilization of the resources. Another variant of the same approach where we are explicitly specifying the sender and receiver is asymmetric addressing. The difference compared to the symmetric addressing is that here we only specify the sender explicitly, we don't specify the receiver explicitly. So only sender explicitly specifies the receiver, sorry. Only receiver is explicitly specified by the sender, but receiver, it doesn't specify explicitly the sender, which basically means that now a receiver can receive the messages from multiple senders. So here is the pseudocode syntax. So like if Q is the sender, then it will specify explicitly the receiver, which is the process P. But in the case of the receiver, let's say the process P, you are not specifying here the ID of the sending process. You are just specifying a variable. And what happens is that P will be able to receive a message, which is destined for P, and then set the ID variable to the ID of the sender process. So let's say if it receives the message from Q, then ID will be set to Q. If received from R or S, ID will be set corresponding to that value. Okay. So in this way, what happens is that a communication link can be shared between between multiple senders and one receiver. But again, everything has its own downside. So if you are sharing the link, then what happens is that it can potentially become a performance bottleneck, right? It depends upon your use case, right? And yeah, this is the drawback of this particular approach here. So also the problem with this whole approach where you are specifying the ID of the sender or the receiver, The problem with this approach is that we are basically doing the hard coding. So here is an example. So let's say I am running an application, which is like multi-process application. It has a sender, it has a receiver. And initially, when I first run the application, the process ID of the P was 1 and the process ID for the Q was 2. Okay. And my Q is sender. So you are now, it is specifying here the process ID of, this is wrong. I think here it should be 1. I will correct it later, but I think you will get the point what I'm trying to say. Just switch the value. Here it should be 1 and here it should be 2. Okay. So here I'm specifying the process ID of the receiver and here I'm specifying the process ID of the sender, right? Now let's say that the application is completed and then at some time, maybe like tomorrow, I again launch the same application. I want to do something and I launch the same application. And this time, you know that process IDs, they don't remain fixed. For every time you run the process, they don't remain fixed. Let's say when you run it the second time, the OS runs different process IDs to these processes. Like process ID of P is changed to 110 and that of Q is changed to 327, but your code is still the same, right? Now, when you will try to say send, actually here it will be 1 and 2. I will switch them later. So what will happen that this process will not be found and your code will, or your application will not run, right? So basically the problem is coming from the fact that you are doing the hard coding, okay? So this is the problem with your direct communication approach, but we can overcome it. How can we overcome? Yeah, if we can avoid this, thing, which basically mean if we have some kind of indirection, I send message, I put a message on the board always stays there. I'm a sender and the receiver get the message from the board. So next time, even if I am like the sender and process, when they are launched again, their process ID is changed, but board is still there. I can again put the message on the board and receiver can get the message from the board. Okay. So again, answering the same question that how sender or receiver, they specify the other process, like how sender specifies the receiver and how receiver specifies the sender. And other option or other approach to answer this question is that instead of explicitly specifying the sender and receiver, we can use the indirect communication where messages are sent to and received from a mailbox or a port. Same example like board, okay? So messages are placed in the mailbox, sender places the message there, and receiver gets the message from the mailbox. So two processes, they have a communication link only if they have a shared mailbox. If they don't share a mailbox, they cannot communicate with each other, and there is no communication link. Also, two processes, they may have multiple links, which basically mean that you can have multiple mailboxes which are shared between two processes, P and Q. Can anybody tell me that what can be a use case where we need multiple links between the two same processes? Like what could be the possible motivation for this? Yes.
So one mailbox be full, so you can use another mailbox to send it to that link to the top.
Yeah, but let's say I say like I have the large enough capacity for that mailbox, then okay, then that use case is covered. But is there any other situation where I would need multiple mailboxes between two same processes? Let's say you are communicating different type of messages between two processes, and maybe one type of messages is more critical than the other type of messages. And also maybe you don't want to, like, if you use the same mailbox, even in the same mailbox you can do it, but let's say in the same mailbox, if you have messages with different priorities, you don't want a message of higher priority to be blocked by a message of low priority, right? So what you can do is that maybe you can have multiple mailboxes, and then the receiver can always first check the mailbox of higher priority. Yeah.
So you're like treating the mailboxes like a priority queue?
Yeah, you can do that, and you can assign priorities to the queue when you implement it. So you can assign priorities to the queue. You can assign priority or even like when you are writing the code, you can develop the logic such that you know that this particular queue is going to hold the high priority messages. So always first check this one. and then the next one, and so in the order of priority. Okay. Okay. A link may be associated with more than two processes, which basically means that the same mailbox can be shared between more than two processes. It is possible that you have one sender and multiple receivers, or you have multiple senders and multiple receivers sharing the same mailbox. So each mailbox has a mailbox is a unique identifier. So basically, the idea here is that the entity which is going to hold the message exists independent of the process, whether it is a sender process or a receiver process. So which basically means that it is possible to keep the mailbox even when your processes terminate. Okay. I mean, again, this is one, let's say, design option. So you can say that the mailbox is going to be owned by a process, or the mailbox going to be owned by the operating system. But then both of these have different implications. Though both of these options, like if you go with the choice one, it has different implications. If you go with the choice two, it has a different implications. Okay. So OS must provide mechanism for creating, deleting, and sending or receiving the messages through the mailbox. And actually, we have an example at the end of the lecture slides. So we'll see that how we can do it in Linux. So this is like graphical depiction of how things work. You have a mailbox, which is administered by the kernel. So sender and the receiver both have to access this mailbox. But in order to place a message in the mailbox, the sender has to invoke the send API, and which basically means that it will trap into the kernel. And then the message will be placed there. And when the receiver needs to receive the message, it will invoke the receive API, which will actually remove a message from the mailbox and give the pointer of that message to the process, to the receiving process. Okay. So by the way, you can here see, if you want to compare it with the shared memory approach, here you can see that whenever you want to transfer a message from the sender to the receiver, you have to make the system calls. But this was not the case in the shared memory region. Once you have created the shared memory region, the OS is not involved. You can simply use the load store instructions to put the data into, like, for example, if you remember in the example you had an array, just give the index of that array and what the value you want to put into that array. There is no OS operating system call involved. Okay. Now the question is, who owns the mailbox? Actually, I have briefly mentioned it already, that you can answer this into two different ways, that either a process is the owner of the mailbox or the operating system is the owner of the mailbox. But if a process is the owner of the mailbox, then which one of those, the sender or the receiver, right? So the process that creates the mailbox, it is going to be the owner of that mailbox, and it is going to be part of its address space. So it doesn't matter whether who create, like the sender can create the mailbox or even the receiver can create the mailbox. But whichever of them creates the mailbox is going to be the owner. And the user, it can only send the messages to the mailbox. And when the owner process terminates, the mailbox will also disappear. It will not exist anymore. And then the sender needs to be notified that if I want to send a message to a mailbox which is not there already, then there should be a mechanism supported by the operating system or by the application developer to specify that this mailbox doesn't exist anymore. Okay. The other case where we say that, okay, operating system owns the mailbox, then our mailbox can exist independent of the processes. So again, but the owner is the one who creates the mailbox, and then the user can only send the messages to the mailbox. As we said, that mailbox can exist independently. So if, let's say, the owner process terminates or dies because of some reason, then the operating system will can potentially transfer the ownership to other processes, which basically mean that there can be multiple owners of the same mailbox over the time, not at the same time, but over the time. Any questions? Okay, so here is another question. Let's say that two processes are communicating with each other, and sender and receiver. And let's say that because of some reason, the sender is not able to send a message or receiver is not able to receive a message. So in this case, then what should be their behavior? Basically, what we are asking is this question, that if sender is not able to send the message, should it keep waiting until the message is successfully sent to the mailbox or to the receiver, or should it be able to proceed without waiting for that message to be delivered, right? So also, to answer this question, we can ask a second question, that what is the nature of our processes which are involved in the communication? Are they able that how to say uh, the use case is it allowed in the use case of those processes that they can overlap the communication with the computation, which basically mean that if I'm sender and I'm not able to, let's say I try to send a message to the receiver, but I'm not able to because of some reason, it fails. Can I do something else while I'm waiting for that message to be delivered, or I can't do anything else? Maybe let's say I want to do some computation, but that computation is dependent upon my successful transmission of the message. If that is the case, then definitely I must wait. But if that is not the case, if my proceeding computation, the computation I want to perform after sending the message is independent of the message, then maybe I don't need to wait, right? So basically, I can, meanwhile the message is being transferred, or it is like, uh, let's say the queue is empty, queue is full. So what I can do is that instead of like waiting for the queue to become empty, I can do something else and then come back and check again, is the queue, there is some slot available in the queue or not. Okay. So if the communicating process, it cannot overlap the communication with the computation, then which it means that sender must block until the message is received by the receiver or the mailbox. By the receiver in case where we don't have the mailbox involved, there is direct communication. But if mailbox is involved, then the message should at least be delivered to the mailbox. And if it is not delivered, then our sender will keep waiting because it must wait because it cannot overlap the communication with the computation. And receiver will also block until it receives a message from the mailbox, or the message is available in the mailbox. So this is known as blocking send or receive. So basically, where the behavior is that you don't proceed until you can successfully send the message or you are successfully able to receive the message. Again, whether you use blocking or non-blocking, we will talk about non-blocking in like a couple of minutes. But again, it depends upon your use case. What is your requirement? Okay. So here is an example. So if we are using the blocking send and receive, one advantage is that it is very easy to synchronize the producer and the consumer, because let's say sender can proceed only after the message is sent successfully, and receiver can proceed only if the message has been received successfully, which basically mean that for the next message to be received successfully, the sender should have been able, like it is one-to-one mapping. So one message should have been transferred successfully before the sender can transfer the next message, right? So here is example. Let's say you have a message, next produced, and off type message. You are simply, this on the producer is simply running an infinite loop. It produces an item which is placed in the next produced, like this is, let's say, pointer. And then we simply say, okay, send next produce, send this message. So now it will be blocked here if like we are using the blocking send and receive. So it will be blocked until this message is successfully received by the consumer, either in the mailbox, or if it is a direct communication, it is received by the processor. So on the receiver side, we will first receive the message. So if there is no message, it will keep waiting. Once the message is received, then the next iteration. So basically, it means that one message is transferred between producer and consumer. Only like second message is transferred between producer and consumer only after the first message has been transferred successfully. So it is easy to synchronize both producer and consumer. Now compare it with the case where, let's say, one of them is not blocking, where basically mean that sender, even if it is not able to successfully send the message, it can do something else and come back and check and retry basically. Okay. the second option where we say that, let's say that we are able to overlap the computation and the communication part of the application. So then we can use the non-blocking variants of the send and receive APIs, where in non-blocking the sender sends the message. If it is a success, then it will come back. The control will be returned back to the sender immediately. If it is a failure, the sender will not be blocked. It will simply get an error status, and then based on that error status, it can retry to send the message. So it is basically not blocked. So maybe you get an error message, but then you say, okay, let me do something else, and then I will try again sending the message. Receiver again does the same thing in non-blocking receive, that it checks whether it tries to receive a message. If the message is available in the mailbox, it will get the message successfully. And if let's say the mailbox is empty, it will not be blocked. It will again get an error message, and then it will continue its execution. And again, it can try again. We will see an example, and then it will become more clear. Okay. Another question which is also related to the same primary question, that whether sender and receiver, how they behave when they are not able to send or receive the message successfully. The second question is related, is that is messaging queue shared among multiple senders or receivers? So maybe let's say if you are sharing, there is one sender, let's say, and there are multiple receivers. So it is possible that now, since there are multiple receivers, you need to synchronize, right? You don't want, let's say, the two receiver processes to trying to get the message from the mailbox at the same time, right? So which basically means that you restrict the access. Only one receiver can access the mailbox at a time. So which basically means you need some mechanism to synchronize the access. Another question is that can the messages be buffered or not? Let's say that sender is producing the messages at a high frequency, but receiver is like, let's say the receiver is not only receiving messages, but it is also doing something else. Okay, and it cannot receive the messages at the same rate as the producer is producing them. So in this particular case, what we need to do is that we need to buffer the messages between the sender and the receiver. Let me finish this slide and then we can take a break. So if we say that messages can be, again, I mean, whenever we ask a question, there can be different options. And then when you say there are different options, then each one of them have their own implications with respect to your, let's say you are designing the system. So with respect to your design, there are different implications. So let's say we say that no buffering is available. So this is known as zero buffering capacity. So in this case, if no buffering is available, then the sender will always block. So we'll always be using the blocking send, right? So if you can successfully send, okay. If not, the sender will be blocked. It will not get an error message, then the control will not return to it immediately until it is successfully able to send the message, because there is no buffer, right? On the other case, if there is buffering available, then the second question is, okay, buffering is available, but what is the capacity of the buffering? So is it bounded capacity or is it unbounded capacity? If it is bounded capacity, then sender will try to send the message, and if there is an empty slot in the buffer, the send will be successful and the control will be returned immediately to the sender. But if your buffer is full, then sender will not able to send the message, and it must wait for the slot to become available and be able to successfully send the message. On the other hand, if let's say there is a case we have unbounded capacity, then sender will never block. So basically here what we are saying is that we will use non-blocking send here. Here we will always use the blocking send. Here will always we also use the blocking send. And as a part of the blocking send, the characteristic of the blocking send is that if you can successfully send, okay. If not, you will be blocked. Okay. Okay. Let's take a break and then we can meet after 8 minutes at 45.
Yeah, I just thought that this thing. The map is like. She's like, setting it up, like, especially when like for it will show that.
One good on Ben on the songs. Should ask Jacob. Yeah, because what you just said, the control, I would like a knife down.
So
Yeah.
So our midterm is almost 2 weeks away, right? I mean, according to the tentative schedule. Hopefully it will not change. I will try to release a simple midterm exam within this week. You can go over it, and so it will give you an idea about the format, difficulty level, and the material that will be covered in the midterm exam will be like 1 week before the midterm exam date. Like, let's say it is according to the schedule, it will be covered up to chapter 4. So week 5, threads and concurrency. But the next chapter, which we will cover before midterm 1, I will try to CPU scheduling. There will be no questions on that in the midterm exam. So you are responsible from chapter 1 to chapter 4. Okay. I will make an announcement also so that it is official. And another thing, I will try to release a questionnaire for my self-evaluation. So please try to participate in that. It will be like, you don't need to specify your ID or your name. So, but it is only for my own, I want to see my performance, teaching performance. Okay. Okay, so we were trying to answer different questions related to the logical design of communication link between between two communicating processes. Like, we asked the questions like how we specify the sender and receiver, whether it is, which basically mean whether it is direct communication or indirect communication. Also, what will happen if sender or receiver, they are not able to successfully send or receive the message, whether there is buffering available or not. So when you answer these questions, you have different options, and as a result of those different options, you have different implications, right? So by the way, I mean, I'm teaching the course, but also at the same time, I think I mentioned it earlier also, I want you to develop this skill that whenever you are like, I don't want you to like take this course and just gather a bunch of information like, okay, we can do communication between processes, like, and then there are two different ways, which by sharing the memory or by passing the messages. But then why we even need, if we can do it using the shared memory, why even I need the message passing, right? So there must be some motivation, right? There must be some problems with the shared memory approach, which is then addressed by the message passing approach. So there is always a structure in the things. So I don't want you to like randomly memorize the information, but track that structure. Okay, so this is basically the table which actually gives you information about how the blocking send and receive or non-blocking send and receive will behave in case of like scenarios where we have buffering or we don't have the buffering. So let's say there is a mailbox, or there is a communication link between sender and receiver, and that is like mailbox is maintained by the kernel. So sender invokes the blocking or non-blocking send, and receiver invokes the blocking or non-blocking receive. And then we are assuming that for the buffer or the mailbox has the buffering capability or not. So let's say you have the 0 buffering capability, and then the next column says you have some buffering capability, but it is not infinite. Okay. So if you are using the blocking send and you have the 0 buffering capability, then the sender must wait until receiver receives the message, right? This is like kind of obvious. You cannot use here non-blocking send. Okay. And in this case, what if you have, okay, let's maybe we can first go to the this column and then we can check the second column. But if you are, and on the receiver side, if you are using the blocking receive, then it will wait until sender has a message to send. If there is no message to send, it will be blocked. It will not be able to proceed. Non-blocking send, if you have 0 buffer, then it will return, will receiver receive the message or error, so which is basically success or failure. But if it is a failure, you will get an error message. You will be able to detect the failure. And which on base of that, you can decide whether to retry or not. And non-blocking receive, again, the receiver will return with a message or a failure. So failure string. Okay. So same for the case when you have like not same but similar like different situations for the case when you have some buffering capability, how the blocking send will behave and how let's say non-blocking is. I will cover only these two and we can move to the next slide. So let's say you have the blocking send. So what happens is that it will your sender will wait until the kernel receives the messages, which basically mean that either the message is received in the buffer, and in that case it will not wait, right? But if it is non-blocking send, so it will wait until the kernel receives the message. If the kernel has not received the message, then it will at least return the error to the sender. Okay. So the basic idea here is that in non-blocking send and non-blocking receive, the process immediately returns, whether it is success or failure, immediately returns. But in blocking send and receive, your process keeps waiting until you are successfully able to send or receive the message. Think about this case on your own. What if how the third column will look like for the case when you have unbounded buffering capability? Okay, so here is an example where we are going to communicate between two processes, sender and receiver, but not through the shared memory, but by passing the messages. So we have a producer and a consumer process. Producer sends the message to the consumer. And in the following example, we will always first, when we are running this application, we will first run the consumer first. So keep this in mind that we are sending the consumer first, but at the end of the example, you need to answer me why we are running the consumer first, why not producer first. Okay. So first we are defining a header file. So in the header file, we first have, we are defining a string, a message queue name, MQ name. And if you look at the value of that, what is this called? Macro. The value of this macro, it is just name, but before that just name, there is a /. So this is the syntax which you need to follow in Linux when you need to specify the name of the message queue, which means basically that it must start with a /, and after that you can write anything like my queue, your queue, whatever. Okay. And then we are defining a structure with the name of item type. You can define like a structure with any arbitrary number of fields and type of fields, but here we are just having two fields. One is the ID, which will basically just give us the ID of the message. And then we have a character field, which is actually an array of character type of size 64. So we'll be putting the message. So basically we will have a message and a message ID. Okay. So like if you have a variable of this structure type, so basically you are saying that each variable represents one message. It's readable, right? Everyone can read? If not, let me know. Contains the definition of different in the code, and also the definition of different functions or APIs like message send or message receive, or you want to check some attribute of the your message queue and so on. Okay. So if we, let's say, like, let me walk you through this code, starting from the main. So first we are just defining some variable of type message queue descriptor. Why I'm doing this? Because I just want you to compare how things are done as compared to the shared memory approach. Okay. So, I mean, there is the reason behind sharing this example. So you are first defining a variable of type message queue descriptor. So the message queue descriptor type is itself defined in the header file, which we have already included. So we don't need to worry about that. but definitely you can go and you can check the manual pages and you will find what are the different fields of this message queue descriptor. Okay, so actually it gives you different, it holds the different fields which gives you the attributes of the message queue, like what are the maximum number of the messages you can hold in a message in a queue, what is the size of each message, and so on, or what is the priority of a message. Okay, so then we are defining a variable of type item type, and we are just naming it item. Another variable n, which we will use to basically hold the return value, which is returned by like different APIs. So we first need to, so this is basically the code for the producer side. And then we have the similar code also for the consumer side, because these are two different processes, right? So we are first opening the, we are calling the MQ open, which is basically a function used to open the message queue. And basically here, first you are specifying the name of the queue, which we have already defined in the header file. And then here we are specifying a flag or specifying the operation that can be performed on this queue. So read write, so we can perform both read operation and the write operation, which basically mean that you can put the message in the queue and you can also retrieve the message from the queue. Okay. Another thing is about MQ open is that you can specify, here we haven't, but you can specify in this function or in the parameters that if the message queue doesn't exist already, create a message queue. Okay, but we are not specifying here. We are assuming that message queue exists already. Okay. Then we are doing the error checking. The MQ open will return you a value, and if that value is a -1, it means that there is something wrong, and you are simply printing a message. Actually, what you can do is that you can also check what is the, like, okay, there is an error, but what is the type of error? So you can find the type of error by printing the error number, which we haven't printed here. But if you want to be like very specific and you want to like find out what is the why there is error, maybe there is not enough memory remain to create a message queue. So then you will get the error number, and then you can check in the error.h, you can go and you can check against each number they specify a brief description of the that error type. Okay, but we are not doing it here. Then we are simply initializing I equal to 0. Basically, we are going to use the I to, we will be keep incrementing it to assign the ID to the messages. Whenever we send a next message, we'll simply increment I and set it as the ID of the message. Then producer is running an infinite loop. And here what you are doing is that first you have already created the item, right? So you are setting its ID equal to I, which is basically initially 0, and you are setting the message part of that item to this thing. OS is good. You can put something, anything what you want, but let's say we always keep sending the same message, but we keep changing the message ID. So this is how we can like differentiate between two messages. And then producer is just revoking message queue send. So here in the parameter, again, you can see more details about this by checking the manual page, but here is like brief description of how it is working. So first you need to specify the descriptor of the message queue, which you have already created, MQ open, which we assume that is already there and we have opened it successfully. Okay. Then the second parameter is the pointer to the message which you want to place into the queue. So we are just simply specifying its address of the item. Okay. So which basically means we are sending both the message and the message ID, right? Third parameter is the size of the message, which is like the size of the item type, right? And then this last parameter is message. Priority range from 0 to 31. Higher the number, higher the priority. 0 means lowest priority. Okay. So which basically means that on the receiver side, let's say if there are multiple messages in the queue, and the receiver says invokes the MQ receive, so it will first receive the message of the higher priority. Let's say there are two messages, one with the priority 1 and one with the priority 0. So the receiver will first get the message with the priority 1. Okay. Then we are simply doing the error checking here again to make sure that message has been sent successfully. So if it is equal to -1, that it's saying something is wrong. What is wrong? You can check it by printing the error number. Okay. And if there is nothing wrong, If something is wrong, we are exiting. If there is nothing wrong, we are simply incrementing the I so that we can use as our next ID for the next message. And then the producer sleeps for 1 second, and then it does the same thing again. It keeps doing in the infinite loop. Okay. Any questions here? Yeah.
Is there any kind, I don't see any kind of condition in code that would ever make this while loop end so that you execute end to close.
Yeah. So yeah, I mean, we wanted to like run in infinite loop, but you are correct. What we can do is that if it is, let's say there is something wrong, what you can do is that you can, instead of saying exit, you can break the loop, and then it will first close the queue and then return it. Okay. Anything else? Okay, so still readable? No. Readable. Okay. So again, I'm skipping the header files, but I'm starting from the main. So this is the consumer side of the code. We have, again, a variable to hold the message queue descriptor, and we are naming it as MQ. We have a variable of type message queue attribute. Actually, every message queue has certain, as I mentioned, has certain attributes like what is the maximum number of messages it can hold, what is the size of the messages, and there are 2 more attributes which I don't remember, but you can go and check. Why we are defining it here? Because we will need it in our code. You will see how we are using it, how we are using the attribute. Then we are also defining a pointer of type item type. So basically what we want to do is that when we retrieve a message, which is of type item from the queue, we want to store it locally. Okay, so that's why we are using this pointer variable. Then we are defining variable n just to hold the return values from different APIs and function calls, buffer length to hold the length of the buffer. And then buffer pointer is again a character variable. So here what we are doing is first we are saying open the message queue. Everything is same. We are providing the MQ name. We are mentioning what operations can be performed, read and write. But then if you look carefully at then we have this OR operation, which basically means that OR with O create, which basically means that if the queue doesn't exist already, create the message queue. Okay. Clear, right? This thing, O create. Okay. And this next parameter 06 is it actually specifies the permissions for the file for all the users, or basically for the queue for all the users. So what we are saying is here basically is 0666. It means that all the users can only read and write the queue. They cannot execute the queue. By executing mean, definitely you will be thinking like, how can a queue be executed? The queue is definitely a code, right? How you implement it is a code, right? So whether we can execute that code or not. So it is not an executable code. And then, now I don't remember, to be honest. You can go and check what is this value of this last, what is the meaning of this last parameter. After that, we are again doing some error checking to make sure that the queue has been opened or created successfully. And if not, we exit. If nothing is wrong, what we need to do is that we first copy the attribute of the message queue in our local variable of type MQ attribute. So we are basically saying that copy the attributes of this message queue into this structure. Okay. And then we read the fields of this structure to find the information about the attributes of the queue. So here we are simply printing that what is the maximum message size. So you can actually here you can see it has a field message queue message size. So it will give you the message size, and then we allocate the enough space for the buffer. So which basically means like, let's say I say like, okay, each message is 1 kilobyte. So if each message is 1 kilobyte, then I'm allocating a local buffer of the same size. So I'm setting buffer length equal to the message size, and then I'm saying, okay, allocate me a memory from the heap of this size. and I'm putting its pointer in the buffer pointer. Now I have a local buffer where I can store the message, which I retrieve from the message queue. And then I'm running this infinite loop on the consumer side. So you are receiving the message, and to receive that, you are again need to specify the message queue from where you want to receive the message. Okay, you retrieve from message from there, but where to put it? So you are putting it in the buffer pointer. You need to also specify the buffer length, so that because the message is copied into that buffer, so the copying operation need to know how many bytes to be copied. And null. So if this the meaning of this parameter is that it actually, remember we said that messages can have priorities, right? So if it is not null, then this parameter will be used to hold a pointer variable, and that pointer variable at that pointer location will be used to hold the priority of the message, which is retrieved from the message queue. So here we are saying that, okay, we are not concerned with the priority of the message. We don't care about it. But if you care about it, you can store the priority. Maybe after retrieving the message, maybe you need to treat messages of different priority in a different way. So maybe in that case, you can use that option. Again, you are doing error checking. If something is wrong, exit. Otherwise, continue. You are simply printing a message that, okay, the message is received successfully and the message size is this one. So n is basically the value returned by this receive. And here, if this call is successful, it returns the size of the message. If it is not successful, it returns the value of -1. And after that, you are printing, since now you have received the message, you have a pointer to it, you can access its ID, and you can also access the content of the message, which always be same, like OS is good, but this will be keep changing, right? And after that, what you do is that you free the buffer pointer. Why? Because we allocated it here, and then there is buffer pointer. Okay, so this is end of the loop. I was like, why we are freeing it in the loop? It should not be. So here is end of the loop. And once we get out of the loop, we must free the memory which we allocated. Otherwise, there will be memory leakage. And then we are closing the queue and we return. Okay? Any questions? No? This is makefile. I'm not going over it. I mean, I assume you know how it works. So, and I'm not going to run the example here, because then I need to first connect with the server and I don't want to waste the time. So, but what you can do is that the code I have given in the slides, it is like simply you can copy paste and you can experiment with it on your own. And what I would like you to do, there are no points for this, but I would love it if you can do it. That implement the project one using the message passing mechanism. Same thing, do everything. Objective is same, but the mechanism is different. So instead of shared memory, you are going to use the message passing. And then if you have read the description of the project one, we want you to draw the normalized execution time as a function of process count, right? So what you can do is do the same thing again for this case, but by using the message passing. And now then you compare it with the graph, which you get in the case of the shared memory approach, and see what is the difference, whether the execution time is more or less compared to the message passing, compared to the shared memory scheme. What are your findings and what is your explanation for those findings? I mean, what are your hypotheses? Why, if let's say the time is more, why it is more? If it is less, why it is less? Okay. So just like to try to think. Okay. So any questions? Okay, so we have some time left. So let me then go over the Let me go over the description of the project. Okay, it is important that you clearly understand what you are required to do. Why? Because the future projects, I plan them to be relevant or to be built upon this project. Okay, so like there is a sequence, like you will be doing maybe similar things or different things, but in different ways. You will be adding some more features to this, Okay, so it is important that you know what you are supposed to do here. So the objective is that you need to know that you understand how inter-process communication works using the shared memory approach. And the description is that, let's say you have a matrix and it is of size m cross n, where m is number of the rows, n is number of columns, right? And what we want to do is that we want to see that we want to calculate the sum of of all the elements of the matrix. Okay, but we want to see that how we can definitely, if the size of the matrix larger, the size of the matrix more it will take to calculate the sum, right? But what we want to see is that how can we speed up the process of computing the sum by using multiple processes. So what we can do is that what you need to require is that you have, let's say, p number of processes. So what you do is that if there are m number of rows, so you divide m evenly among those processes. So you divide m by p. Let's say you have 100 rows in the matrix and you have 4 processes. So you assign 25 rows to each of those processes. So first process is responsible for calculating the sum of first 25 rows. Second is responsible for next 25 and so on. Okay. So you're distributing the work among the processes. But then we need to calculate the total sum, right? Overall sum. So then whatever partial sum is calculated by those processes, you need to sum those partial sums together to find the total, the overall sum. Okay. So how you can do that? So first you need to have a parent process which is responsible for creating a shared memory segment. Actually, 2 shared memory segments. So first shared memory segment, which I'm naming as MS1, and this MS1 should be large enough to hold your matrix. Like, let's say if your matrix is 1024 cross 1024, and each element is of type integer, so the size of the matrix will be 1024 cross 1024 cross 4, right? The size of this shared memory area should be that one, okay? And the second memory segment, actually it is needed to hold the partial sum calculated by each of those child processes. So parent is following the example where we have 4 processes. So you have 1 parent process and 4 children processes. Okay, so this second memory segment area, it should be able to hold 4 partial sums. Now, depending upon how many rows are assigned to each process and what are the values of each of those elements, the range of the result in the partial sum, it may be larger than integer, right? So you need to be careful with that. Then the parent process, after doing this, after creating this shared memory segment, the parent process will create, it will create and launch C number of children processes. Like in our example, C is 4. So it is supposed to launch 4 children processes. And then each child process is responsible for one part of the matrix, like some, as I said, 25 rows, and so on. What you are given? Everything clear here? Right? So what you are given is that you are given following files, but they are not complete. They have some part is available, some part is missing. Project1.h, which basically contains some code which is used both which is shared among children processes. Project1.c, actually basically it is the parent process, okay? And child process, it is the code for the child process, right? And yeah, what you are required to do is that you need to complete the skeleton, the missing part in all 3 files. So how you find that what is missing, I have put the comments, and those comments start with to do. So if something is starting with to do, it's when you need to complete it. So there are 7 missing parts in project1.c and 1 missing part in project1.h and 1 in child process.c. Okay. And after completing these missing parts, you should be able to run the executable file of the project1.c for number of processes set to 1, 2, 4, 8, 16, 32, 64 up to 256. Okay. You are increasing the number of processes and power of 2. And then you need to draw a graph. So actually I have also given you an Excel file. There is a table, there is a graph. You just need to fill that table. The graph will be generated. And then you need to draw that graph. And also you need to write a 4 to 5 sentence explanation of the results you see. I mean, why the pattern, whatever the pattern is, why it is the way it is. So deliverables, you need to complete the source code, evaluation point 60 for that, for all 3 files, okay? Actually, the 2 and 3 are dependent upon 1. If you are not able to complete successfully the code, you will not be able to successfully generate the graph, and you will not be able to explain your results, okay? Submit everything in a zip file. And yeah, that's it. So here is what we are saying, that I have drawn the graph not for 256 processes, but only for 64 processes. So what I have seen on the y-axis, I have normalized execution time. So execution time is normalized. Execution time of for all the process count case is normalized to the case where I have only 1 process. Okay. And what we see is that as we increase the process count, our execution time is reducing, right? But remember that maybe the results in your case, if you even reproduce this example, maybe result in your case are different. Why? Because the machine I'm using, it has 80 cores. So in that case, I mean, it is understandable that it will keep increasing or decreasing. But maybe if, let's say, you have lesser number of cores, let's say you have only 8 cores, maybe beyond 8, it will not reduce. Okay. Or even maybe it slightly increases because of the context switches. Okay. So you are not like, don't force your results to be reversed. Show whatever you get and then explain why you get it. Okay. Anything, any questions? No? Okay.